assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
In this example, we want to determine the magnetic flux through 5 different surfaces on this object I've drawn here. Given that we have a magnetic field that is pointing in the y direction with a magnitude of 0.25 teslas. So we also have all the lengths of our 5-sided object here, and we're going to use those to calculate our fluxes. So I'm going to label each of these surfaces. This back one I'll call 1, and we'll start with that. So for 1, we can see that if our surface normal for this surface points like this, that it's going to be parallel to our magnetic field. So the expression for the flux through surface 1 is going to be BA times the cosine of the angle between the surface normal and the field. But in this case, that angle is just 0. So we know that this is just E times the area of that surface, which we'll call area 1. And area 1 is just going to be 0.3 times 1.2, right? Because it's just a rectangular surface. So this should be 0.25 teslas times 0.3 meters times 1.2 meters. And if we calculate that, we will get 0.09 Webers. So there's the flux through surface 1. Now let's look at surfaces 2 and 3, which I'm going to say are these side surfaces here. So 2 is here, and then 3 will be the surface over here on the ZY plane. And again, just imagine that our surface normals are pointing in towards the center of our shape here. And we can see that for surface 2, if our vector points in like this, and the magnetic field points in y like this, there's going to be a 90-degree angle between these two vectors, which means that the flux is going to be 0 through that surface, since the cosine of 90 degrees is 0. So right off the bat, we can say the flux for the second surface is going to be 0. Similarly, by the exact same argument, we can imagine from the other side, right, or surface here, for surface 3, the surface normal would look something like that. The magnetic field would be pointing this way. And again, there would be this 90-degree angle between these two vectors. So we will say the flux through surface 3 is also 0. All right. So surface 4 is going to be this, we'll say the bottom surface here. And again, let's look at the direction of the surface normal for that surface. So it's going to be pointing up in the z direction. And the B field is going to be pointing in the y direction like this. So again, there's a 90-degree angle between the surface normal and the magnetic field. So the flux for 4 is also 0. Okay. Now for the most complicated one. So surface 5 will be the slanted surface out here. All right. So this surface we can see is going to have at least some portion of it will be parallel to the magnetic field, right? Some portion of its surface normal. So if we draw that surface from the side view, something like this, we can see that the normal of our surface is going to point up in this direction. And the magnetic field, as always, is just pointing in the y direction, which is this way. Just to be extra careful and specific here, our axes are y and z in this view. And so now what we're interested in to calculate the flux is going to be this angle here between this surface normal and the magnetic field. And once we know that, if we have the area of our surface, which we should be able to figure out from our drawing, yes, our area will just be 1.2 times 0.5, right? Since it's just a rectangle. So we'll just do width times length. So we pretty much have everything we need to calculate the flux for 5. We have B, we have the area of the fifth surface. We just need to figure out what the cosine of the angle between these vectors is. All right, so there's a couple ways to think about this geometry here. And the way I'm going to do it is like this. Imagine we draw some axes here on our triangle, something like this. And now imagine that we rotate our axes so that the y-axis here is parallel with the slope of our triangle, and the z-axis is perpendicular to it. So it would look something like this. So that angle we would have rotated it by would be theta right here, which we can see is going to be the exact same angle as this here, right? Because this line moves away at the same time this line would move away from that axis. And the angle we want to find here is actually this angle, theta 2, right? Because we want to know the angle between the normal of our triangle, which is going to be the direction of z prime here along our new axis, and y. And theta 2 is just going to be 90 degrees minus that angle theta. So that's one way to think about it for a triangle. So if we find this, we look up at our triangle over here. If we were to find this theta right here, and we take the cosine of 90 minus that theta, we'd be ready to go. Alternatively, we could realize that this angle up here is just going to be theta 2, and we could use that one instead. Either way, we're going to have to solve for an angle. So I'm going to solve for theta real quick, and we can do that by using the tangent of theta, right? So the tangent of theta is just going to be 0.3 meters over 0.4 meters, right? Opposite over adjacent. And then we'll take the arctan to get our angle. And that angle ends up being about 36.87 degrees. And we said that theta 2 is going to be 90 minus that. Which is about 53.13 degrees. All right. So if we use that angle for theta, for the area, we said it was just going to be 1.2 times 0.5 meters. And then B is the same magnitude as always, 0.5 teslas, 0.25 teslas. We will get for our final flux here a value of 0.36 weathers.